Hello everyone. Too bad we can't be together. Kind of miss you guys, but let's just try the best we can with what we've got here. It's been a long time since I've talked to you, and I'm not 100% sure where we left off because it was such a long time ago, but I believe that in the last class we had covered section 7.3, doing confidence intervals for a population mean. And then we had our quiz. I've got your quiz grades posted in Moodle. I've got all your hard copies, but it just isn't going to work for me to scan them all and send them all to you. So I'm going to just give you, in my email, I'm going to attach the quiz and the solutions to that. And if you have a question about your individual quiz, I guess you just have to sort of try to remember what you took. And I do have them with me, so I could look that up, possibly. Also, I have some grades in for your project, and the project was about where you make your own game, and the games were great. The games were really interesting. They were fun, but a lot of you didn't really do a very good job on getting the most important part, getting the probability mass function. So the rubric that I used was 6 points for your game and your game description, 2 points for getting the correct probability mass function PMF, and then a point each for doing the, I guess it was 5 for the, 5 for the overall game, and then a point each for getting the mean, the standard deviation, and the simulation correct. And then it's possible that for some game that you were thinking about, you might, most of you did have it correct, but for some of you, the PMF that I saw just didn't seem to agree with the game that you were describing. And so I would have taken the 2 points off there, or part of those, at least part of those 2 points off. So anyways, but let's move on. So that takes us to chapter 8, and in the book, the first 3 sections of Chapter 8 deal with doing hypothesis tests for a population mean. The first section assumes that your population standard deviation is known, and it kind of goes through all the theory of that. And I think it's good to read the 8.1. However, in real life, you really never know the population standard deviation. So that's not actually how you do hypothesis tests. It's kind of like what we did when we did confidence intervals, that at first we assumed that the population standard deviation was known, then we went to the unknown. Well, we don't have as much time to deal with things now. I'm going to kind of focus on section 8.3, and then hopefully you can watch this video. I'm going to try to keep it brief because I'm actually running out of space in my Google Drive. I'm going to try to keep it brief, but also I have another video that I'd like you to watch, and I'll put that in our Moodle site, although Moodle does not seem to be working right this second, but when it is up, I'll put that in there. All right, so anyways, here's the thing, that sometimes when you're doing hypothesis, when you're making inferences about the population from the sample, sometimes you just want to get a range of plausible values. I think that's kind of the most typical thing you might want. But sometimes you actually have to make a decision. Sometimes you have to make the decision, does this treatment actually improve the patient's well-being or not? And sometimes, like in courtroom, there's actually even statistics come in there. I've actually been an expert witness doing statistics in a courtroom on a discrimination case. Sometimes in the courtroom, you actually have to make a decision. Is the person guilty or not, or you find them not guilty? And hypothesis testing is kind of our statistical approach for doing that kind of thing, making decisions. It's not a perfect approach. It's a protocol that's been built up over years. It's got some limitations, but it's what most people do. And so we're going to kind of take the standard approach to doing it. And the important thing to remember in hypothesis testing is it's not just the decision that matters, it's following the protocol appropriately, so that if anybody else gets the data can always be misleading. You can have data that's very unusual, something that's very rare, in which case you can lead you to the wrong decision. But as long as you follow the appropriate protocol and anybody else given that data would make the same decision, you've done the right thing. All right, so in this example I'd like to start with is in the following, and rather than read it all out, I'm going to let you read it. A lot of times when I ask questions or ask you to kind of read something, you could just put it on pause, read it, and then come back to it later. All right, so in this situation, we've gotten this data from, I think we talked about it earlier in class. This is data where students looked up the tuition at, I forget how many it was, let's see. I think it was, let's assume it was 30 schools. Unfortunately, Minitab is not working right now either, so I'm not able to rerun this on Minitab. Let's say there's 30 schools, and they had a sample mean of 18,032 for tuition and a sample deviation of 10,332. So we want to make a decision, is this not the same, this mean of all the out-of-state tuition for all the state school, public schools, is that not the 19,738? That's which UNCA's out-of-state tuition. To answer this question, and like in Hull hypothesis test, I'm going to break it up into 4 steps. I believe in the one video I'm having you watch, he does the same thing, but he calls it 5 steps. But I think it's basically the same thing. All right, so the first step is kind of your setup step. To set up the null hypothesis alternative and state with alpha, which is your significance level. So what is the null hypothesis? The null hypothesis is what you'd be willing to believe until you're shown otherwise. Sometimes it's called the status quo, or that there's no difference from what was previously thought. That's your null hypothesis. The alternative is what requires evidence to support. In many cases, that alternative is the research hypothesis. It's like you're a researcher, you're trying to show something new that the world doesn't know yet, and that thing that you're trying to show them would be your alternative hypothesis. It also has an analogy in the courtroom. What you'd be willing to believe until shown otherwise, I hope you would say, is that the person is innocent, and then the alternative is that the person is guilty. The significance level is very closely, if we call it alpha, and it's very closely related to the confidence level that we had in confidence intervals. But the significance level is the probability of making a mistake. In particular, it's the probability of making the mistake of rejecting the null hypothesis when it's true. And we're going to go into a little bit more on that later. It turns out that there's kind of 3 basic setups that you can have for your null and your alternative. You can have, on the left, you can have what we call the less than alternative. The greater than alternative. You can have a less than alternative, or you can have a not equal alternative. And you can get these from the wording of the question. In this question, it's phrased, does the data show, the question here, does the data show that the mean number of out-of-state, the mean out-of-state tuition is not 19,738? Because the data says is not, that translates directly into not equals, so the appropriate alternative, null and alternative, is right here. Now let's get our notation down a little bit. Mu by itself stands for the population mean. That's something that you actually never will really know. It's something that you hypothesize and make decisions about, but you never really know what it is for sure. So we never have a number in for the mu. The mu sub 0, or sometimes known as mu naught, is the hypothesized mean. That's the status quo mean. That's what you're trying to compare it to. That's what you think it might be until you're shown otherwise. In this case, and that's always given in the wording in the problem. In this case, the null hypothesis is the number that we're comparing the mean out-of-state tuition to, UNCA's tuition, 19,738. So that is our hypothesized value. So in this case, our null is that the population mean is the 19,738 versus the alternative that the mean is simply not equal to 19,738. Once you've got that, then you can calculate your test statistic based on your statistics. So let's plug it in there. Since our sample mean was 18,032 minus a hypothesized mean of 19,738 divided by the standard deviation that I'm assuming is 10,332, and divide that by the square root of n, and our n I'm assuming is 30. I'm just trying to remember as best I can since I can't access Minitab right at this second and I need to get this out to you. All right, let's calculate that out on our calculator here. So, all right, I guess the best way to do it is parentheses. And I'm getting, for my test statistic, negative 0.904. Notice that here we are using the t statistic. If we knew the population standard deviation, it would be the z statistic. But because we don't know the population standard deviation, we have to replace it with a sample standard deviation, s. That puts it into in a situation that's a little more variable, and it's what gives you what's called the t statistic. And the t statistic has a little more area in the tails than the z. As your sample size gets larger and larger, your t statistic gets closer and closer to the standard normal. Depending on your sample size, you'll have a different t distribution. As the sample size gets larger and larger, your t distribution gets closer and closer to the standard normal. In this case, with 30, it's going to kind of differ a fair amount. So unfortunately, to get the next step, we're going to have to use technology to get the next step. And the next step is to get what we call the p-value. You could get a rough idea of it, and you could get a rough enough idea to make a decision about which one you're going to, whether you're going to reject the null hypothesis or not, from your t table. But it's really hard to get an exact p-value from the table, so I'm recommending that we're going to use technology to get the p-value. But here's the theory behind what our technology is going to do. In this case, because we had a not equal alternative, and the p-value always stands for the probability of getting the null let's try this again. The p-value is equal to the probability of getting your stat, your t statistic, or one more contrary to the null, if the null is really true. It's pretty hard to think about that, but let's just go with that for now since we're kind of running short on time. So the p-value here is negative 0.904. The t, like the z, is centered at 0. There's two ways you could get something more contrary to the null than the one we've got. If we got something less than negative 0.904, that would be as contrary. But if we got something great as 0.904 or more, that would also be as contrary. So the p-value is really the sum of these two probabilities of these two regions. Let's do it on our calculator. I'm going to stop this video now, and I'll pick up on another video so that they don't get too long. So I'm going to pick up on the next part of this in just a minute.